everyone, Rhoda here with a JAC capsule about exponential functions. First of all, we have in front of us the most basic form of an exponential function, y equals a to the power of x. A is our base. That can be whatever number we choose, as long as it is positive. So a is some positive value. And then we get our exponential function where we're going to take in some x value, we're going to calculate a to the power of that x value and get a y value as our answer. So just to quickly remind you how that works, if x is some positive whole number, then a to the power of x would be a times a multiplied together x times. So it's just a times itself, x times. Or you could remember this other important property. If we have a negative exponent, that is going to create a reciprocal. So you could say a to the negative x is actually the same thing as 1 over a to the positive version of x. And then again, if x is a whole number, this would be 1 over a times itself, x times. These are the basics that I need for this topic here, which is going to be the graph of exponential functions. But if you're looking at this and you think you need to go back and review the properties of exponents in general, we do have a whole playlist of videos about that you can check out. For now, I just want these two, because what I want to talk about is what does the graph of this function look like? So if I write down y equals 2 to the x, and I ask you to picture the graph, is there a picture that comes to your mind or not? And if there is a picture that comes to your mind, can you explain where it comes from? Does the graph make sense to you? That's what we want to look at here. And to think about that, we really just need these two properties of exponents that I wrote down. Now, what if I asked you just in general about the graph of y equals a to the x, and I don't tell you what the base is? Is there still a picture that comes into your mind? Is there a graph that you know it's going to look like? Or are there a couple of options? Well, there are a couple of options depending on the value of your base. So I want you to figure out, what does the graph of an exponential function y equals a to the x look like in these two different cases? The two cases are when our base is bigger than 1 and when our base is less than 1, but it still has to be a positive number. So between 0 and 1. If you already know that, that's fantastic. You could maybe skip this video and go to our problem set. If you don't, let's start with an example. Let's try to figure out the case when a is bigger than 1 by figuring out the graph of y equals 2 to the x. So you could try to figure out the graph in whatever way you're most comfortable. If you're not sure where to start, I would recommend setting up a table of values. So that's what I'm going to do below. Before I draw the graph, I'm going to create a table of values. This will help me understand what 2 to the x is doing at different values of x. So I'm going to fill in some x values that I'd like to do. Let's do x equals 0, x equals 1, x equals 2, x equals 4. And then let's go into the negatives. We'll do x equals -1, x equals -2, x equals -4. Pause the video here and fill in this table of values on the right-hand side. Find all the y values that go along with these. When you unpause the video, I will have already filled that in. So here's my table of values all filled in. I now have 7 different points that I know lie on the graph of y equals 2 to the x. I just want to notice a couple things. So when x is equal to 0, I had 2 to the power of 0, which is 1. And that really would have happened no matter what base I choose. For any a, I would have had a to the power of 0 is equal to 1. So that tells me that I'm passing through the point x equals 0, y equals 1, and I would have passed through that point for any base. It didn't have to be 2. Any base passes through that point. That's an important fact to know. Moving on, when I plug in these positive values, all I really notice is that the values are increasing. So when x is 1, I had 2. When x is 2, I had 4. When x is 4, I got 16. If you want, you can think about what's going to happen as you continue on. And if you do, you're going to realize that these numbers are going to start growing very, very fast. So I didn't do this value, but if I add an extra one, if I tried x equals 10, then y would be 2 to the power of 10, which is 2 times 2 times 2 times 2, 10 times, which I think about for a second. I can tell you that that is 1024. So this thing is growing really, really quickly as my x values increase on the right-hand side. So positive x values are giving me larger and larger and larger y values as I go. And that's usually what people mean when they talk about exponential growth. They're talking about as your x values get larger and larger, your y values are shooting up very, very quickly. What about the negatives? Well, when I evaluate the negative exponents, I have to use that property that a to the power of a negative number is going to be the reciprocal of a to the positive version. So when I plug in x equals -1, 2 to the -1 becomes the reciprocal of 2, so 1 over 2 to the power of +1. And same goes for all of them. So what ends up happening is whatever number I'm plugging in as my exponent, for example, when I plugged in -4, it's as if I plugged in the positive version, but then I had to flip my answer around. So that's why you see for -4, I got an answer of 1 on 16. For +4, I got an answer of 16. What is that going to do to my graph? Well, as my x values become bigger and bigger negative numbers, now I would have 1 over larger and larger and larger numbers. So what happens when I have 1 over a very, very large positive number? If it helps, you can think of the example. If we do x equals -10, we would have y equals 2 to the power of -10, which would be 1 over 2 to the power of +10. So that would be 1 over 1024. So as my x values become very big negative numbers, my answers are going to be 1 divided by a very large number. That's going to give me a very small number, but it's still going to be positive because I have a positive number divided by another positive number. Great, so I see some patterns here. I could plot these points on my graph, but I could also just notice 3 facts. This graph is going to pass through the point 0, 1. On the right-hand side, it's going to grow very quickly. On the left-hand side, it's going to have smaller and smaller and smaller values as x becomes a bigger and bigger negative number. But those small values are always going to be positive. They're never going to reach 0. They're just going to get closer and closer and closer to 0 as I move out to the left. They'll never be 0 and they'll never be negative. That's enough to give me the rough sketch. And this is the image that should pop into your head if somebody mentions the graph of y equals 2 to the x. Or really, if somebody mentions any graph y equals a to the x when a is a number greater than 1. So going back to my graph, I can plot the points and sketch my function y equals 2 to the x. I know that it's going to pass through the point 0, 1. On the right-hand side, as the x values increase, my y values increase very, very quickly. That's what we call exponential growth. On the left-hand side, as I have bigger and bigger negative x values, my y values are decreasing towards 0. They're never actually going to reach 0. They just get closer and closer to 0 as we go. That's called a horizontal asymptote. We have this line, y equals 0, which we're getting closer and closer and closer to, but we're never actually going to end up there. So here's my graph for the exponential function y equals 2 to the x. And there are a few important properties here that I want to point out. First one, I noticed that this graph passes through the point 0, 1. And we noted that this would have happened no matter what base we chose, because any a to the power of 0 would give us y is equal to 1. Next, notice that this graph is always above the x-axis. So the y values are always strictly positive. We never have y equaling 0, and we also never have a negative value for y. That's also true for every single exponential function. So the things we noticed here are going to be true no matter what base a we might choose. This is true for all exponentials. There are a couple other properties that I notice here that aren't always true, but they're true for the case when our base is greater than 1. Anytime your base is greater than 1, we're going to see the same behavior that we have for 2 to the power of x on the left and on the right-hand side. So on the left, the y values approach 0. We've got that horizontal asymptote at y equals 0. And on the right, the y values are increasing extremely quickly and becoming large positive numbers. These facts are true for every exponential function that has a base greater than 1. Now, the second case to consider is what if that base is not greater than 1? So what if the base is something less than 1? Well, let's try that example now. So we'll take the example y equals 1/2 to the power of x and try to figure out what the sketch is. So just like before, we can start with a table of values if you're not sure how to sketch it. If you already know how to sketch it, you can skip this part. But if you need the practice, try to fill in this table of values. So once again, pause the video, and when you come back, I'll have these values all filled in. So here it is all filled in. What can I notice? Well, first of all, I notice that when x is equal to 0, I still get y equaling 1. That's what we said would happen. We noted that anything to the power of 0 will give 1. That means all exponential functions are going to pass through the point 0, 1. For the rest, we can actually see that if we compare this case to 2 to the power of x, we have flipped all of our answers. So 1/2 to the power of 1 gives us 1/2, and 1/2 to the power of -1 gives us 2. Well, that's the opposite of what we saw for 2 to the x. So the answer for x equals 1 and the answer for x equals -1 have been exchanged. And that's happening because when I apply a negative exponent, I'm taking the reciprocal of my base. So 2 becomes 1/2, or 1/2 becomes 2. If you think about it that way, then it makes perfect sense that for all of these points, whatever happened with 2 to the x, now we're getting the reciprocal answer. With 2 to the x, we had 2 to the power of 10 equaling 1024, for example. With 1/2 to the power of 10, we get 1/1024, and so on for all of them. So when we plot this graph, here's what we're going to get. So I've plotted my points, and what I can see is I have the same basic idea as before. I'm still passing through the point 0, 1. I'm still getting very large y values very, very quickly on one side and very, very small positive y values on the other side. But those two sides have flipped compared to 2 to the power of x. So now I have my horizontal asymptote at y equals 0, but it's on the right-hand side. And I have this exponential increase, or really it became a decrease, on the left-hand side. So the two images are just mirror reflections of each other. These are the two cases of exponential graphs. So when my base is less than 1, it's going to look something like this. So here are my main takeaways. For any exponential function y equals a to the x, we know that the graph is going to pass through the point 0, 1, and that the y values will always be strictly positive. Also, depending on the base, we have two cases. If the base is greater than 1, then we know that our graph is going to look like this. On the left-hand side, the y values will be getting closer and closer to y equals 0. We have a horizontal asymptote, but we never reach y equals 0. We're always a positive number, even if it's a very small one. On the right-hand side, my y values are growing extremely quickly. That's called exponential growth. Or if my base is some positive number less than 1, we get the same graph but reflected across the y-axis. So that means that my very small positive y values are on the right-hand side now. My horizontal asymptote has flipped to that side. And I see that very, very, very steep change in y value happening on the left now. So that's your summary. What should come into your mind when you think about an exponential function? To try that out, you can head on to the next video or look at our posted problem sets.